Download this code from codegive.com, link in the description below. OK, here's a detailed tutorial on building an advanced retrieval augmented generation (RAG) system using neo4j as a knowledge graph. This tutorial will cover the core concepts, setup, code examples, and potential improvements. Introduction, RAG and knowledge graphs. Retrieval augmented generation, RAG is a technique to enhance the capabilities of large language models, LLMs, by grounding them with external knowledge. Instead of relying solely on the information embedded in the LLM's parameters during pre-training, RAG retrieves relevant information from a knowledge base, or other data source, at the time of inference. This retrieved context is then fed to the LLM alongside the user's prompt, allowing the model to generate more accurate, specific, and contextualized responses. Knowledge graphs, KGS. A knowledge graph is a structured representation of knowledge that uses nodes and relationships to connect entities, concepts, and attributes. Unlike simple keyword-based searches, KGS allow for semantic understanding and the ability to reason over relationships. Why use neo4j for RAG? Rich relationships. Neo4j is a graph database that excels at managing and querying interconnected data. This is crucial for RAG, where understanding relationships between concepts can significantly improve the retrieval of relevant context. Cipher query language. Neo4j's cipher query language is designed for intuitive graph traversal. It makes it easy to find related entities, explore paths, and extract the specific information you need for RAG. Scalability. Neo4j can handle large and complex knowledge graphs, making it suitable for RAG systems dealing with extensive amounts of information. Semantic search. Neo4j integrates well with vector embeddings and semantic search techniques, allowing you to find nodes and relationships based on meaning, not just keywords. Graph algorithms. Neo4j provides graph algorithms, example page rank, shortest path, community detection, that can be used to identify important nodes and relationships in your knowledge graph, which can be helpful in prioritizing relevant information for the LLM. 2. Architecture and workflow. The basic architecture of a RAG system using neo4j as the knowledge graph is as follows. 1. Knowledge graph creation / population. Data source. You start with your source data, documents, articles, websites, databases, etc. Extraction and transformation. Extract relevant information from the data and transform it into a structured format suitable for the KG. This might involve named entity recognition, NA, relationship extraction, and data cleaning. Graph loading. Load the structured data into neo4j as nodes and relationships. 2. Embedding generation and storage. Node content embedding. Generate embeddings, vector representations, for the content associated with nodes in your knowledge graph. This could be descriptions, summaries, or even entire documents. These embeddings capture the semantic meaning of the content. Embedding indexing, optional, but recommended. Store the embeddings in a vector index, example Fayus, Annoy, Milvus, for efficient similarity search. Embedding storage in neo4j. While optional, storing the embedding vectors directly in neo4j as node properties can sometimes simplify the architecture and improve integration. 3. Query processing and retrieval. User query. The user enters a question or prompt. Query embedding. Generate an embedding for the user's query. Similarity search. Perform a similarity search, using the query embedding and the vector index, to find the most relevant nodes in the knowledge graph. This is often called semantic search. Asterisk context retrieval asterisk based on the relevant nodes identified, retrieve related nodes and relationships from neo4j using cipher queries. This step is crucial to provide the LLM with a rich context. Strategies can include asterisk neighbor retrieval asterisk retrieve nodes directly connected to the most relevant nodes. Asterisk path traversal asterisk traverse the graph to find nodes connected through specific relationships or paths. Asterisk subgraphs asterisk extract relevant subgraphs from the knowledge graph. For augmentation and generation asterisk. Asterisk context augmentation asterisk combine the retrieved context, nodes, relationships, text, etc., with the user's original prompt. This can be done through simple concatenation, more sophisticated prompt engineering techniques, or template-based approaches. Asterisk LLM generation asterisk feed the augmented prompt to a large language model, LLM, example GPT-3/GPT-4, Llama 2, Palm 2. Asterisk response generation asterisk the LLM generates a response based on the user's prompt and the retrieved context. 5. Refinement and iteration asterisk. Asterisk evaluation asterisk evaluate the quality of the generated responses. Asterisk improvement asterisk continuously improve the RAG system by asterisk fine-tuning the LLM with RAG specific data. Asterisk optimizing the knowledge graph structure. Asterisk refining the embedding generation process. Asterisk improving the context retrieval strategies. 3. Implementation example, Python. This example demonstrates a simplified RAG system with neo4j. We will use the following libraries. Asterisk neo4j, neo4j driver for Python. Asterisk sentence underscore transformers, for generating sentence embeddings. Asterisk LangChain, optional, but recommended, for managing the LLM interaction. 1. Setup and dependencies. 2. Neo4j configuration and connection. 3. Knowledge graph population, example. Let's create a simple knowledge graph about movies and actors. 4. Embedding generation and storage. 5. Semantic search and context retrieval. 6. LLM interaction, using LangChain. 7. RAG pipeline. Complete code, for copy-pasting. Important notes. Asterisk replace placeholders asterisk make sure you replace placeholders like your underscore neo4j underscore password and your underscore OpenA underscore API underscore key with your actual credentials. Asterisk neo4j indexes asterisk to ensure efficient semantic search, create a vector index on the embedding property. Use neo4j Bloom, the neo4j browser, or the neo4j CLI. The following code will do it, assuming your embedding dimension is 384, the dimension of all many LML6v2. Asterisk vector index creation time asterisk creating the vector index in neo4j can take some time, especially with a large dataset. Asterisk error handling asterisk add comprehensive error handling to your code, example handle neo4j connection errors, LLM API errors. Asterisk data loading asterisk for real-world applications, you'll need robust data loading and transformation pipelines to populate the knowledge graph from your source data. Asterisk prompt engineering asterisk experiment with different prompt templates to optimize the LLM's response. Asterisk LangChain asterisk consider using LangChain more extensively. It provides abstractions for managing LLMs, prompts, and chains, which can simplify your RAG pipeline. 4. Advanced techniques and considerations. 1. Dynamic context retrieval asterisk. Asterisk adaptive hops. Asterisk adjust the number of hops in the graph traversal based on the complexity of the query or the relevance of the initial search results. Asterisk relationship filtering. Asterisk specify the types of relationships to traverse when retrieving context. This can help you focus on the most relevant connections. Asterisk query expansion. Asterisk expand the user's query with related terms or concepts to improve search recall. 2. Node ranking and prioritization. Asterisk graph algorithms, page rank, community detection. Use graph algorithms to identify influential nodes in your knowledge graph. Prioritize these nodes when retrieving context. Asterisk similarity scores. Asterisk use the similarity scores from the semantic search to rank the retrieved nodes. 3. Fine-tuning LLMs. Asterisk RAG specific training data. Asterisk create a dataset of question-answer pairs, where the answers are grounded in your knowledge graph. Use this data to fine-tune the LLM for RAG tasks. Asterisk LoRa, low-rank adaptation. Use parameter-efficient fine-tuning techniques like LoRa to adapt the LLM to your specific RAG domain without requiring extensive computational resources. 4. Hybrid search. Asterisk combining semantic and keyword search. Asterisk combine semantic search, embedding based, with traditional keyword search to leverage the strengths of both approaches. Asterisk BM25/TF-IDF. Asterisk use BM25 or TF-IDF to find nodes that contain the keywords from the user's query. Asterisk fusion techniques. Asterisk use techniques like reciprocal rank fusion to combine the results from semantic search and keyword search. 5. Knowledge graph structure optimization. Asterisk schema design. Asterisk carefully design the schema of your knowledge graph to accurately represent the relationships between entities and concepts. Asterisk node enrichment. Asterisk add additional attributes to nodes, example summaries, keywords, metadata, to improve search and context retrieval. 6. Vector databases. Asterisk Pinecone, Weaviate, Milvus. Asterisk consider using specialized vector databases like Pinecone, Weaviate, or Milvus for storing and indexing your embeddings. These databases offer optimized performance for similarity search and can handle very large data sets. Asterisk integration with neo4j. Asterisk integrate the vector database with neo4j. Store the vector embeddings in the vector database, and store the node IDs in neo4j. Use semantic search to find the closest node IDs in the vector database. Use the node IDs to find the specific nodes and context information in neo4j. 7. Evaluation metrics. Asterisk relevance. Asterisk measure how relevant the retrieved context is to the user's query. Asterisk accuracy. Asterisk measure how accurate the generated responses are. Asterisk faithfulness. Asterisk measure how well the generated responses are grounded in the retrieved context. Asterisk coherence. Asterisk measure how well the generated response is written and if the answer follows the question. Potential challenges and mitigation. Asterisk knowledge graph construction. Asterisk building and maintaining a high-quality knowledge graph can be challenging. It requires careful data extraction, transformation, and schema design. Asterisk embedding drift. Asterisk the meaning of words and concepts can change over time, leading to embedding drift. Regularly regenerate embeddings to address this issue. Asterisk computational cost. Asterisk generating embeddings and performing similarity search can be computationally expensive, especially for large knowledge graphs. Asterisk hallucinations. Asterisk LLMs can sometimes generate responses that are not grounded in the retrieved context or that are factually incorrect. Careful prompt engineering and fine-tuning can help mitigate this issue. 6. Conclusion. This tutorial has provided a comprehensive overview of building a RAG system using neo4j as a knowledge graph. By leveraging the strengths of neo4j's graph database capabilities and the power of LLMs, you can create intelligent applications that provide accurate, specific, and contextualized responses to user queries. Remember to continuously evaluate and improve your RAG system to achieve optimal performance and address potential challenges. Experiment with the advanced techniques and considerations outlined in this tutorial to build sophisticated and robust RAG solutions. Okay, let's dive into building an advanced retrieval augmented generation (RAG) system leveraging knowledge graphs in neo4j for enhanced question answering. This tutorial will be comprehensive, covering the core concepts, the setup, the code implementation, and the rationale behind the choices. We'll assume you have a basic understanding of Python, natural language processing, NLP, and databases. The power of knowledge graphs in RAG, why and how. Traditional RAG systems often rely on embedding semantic similarity to retrieve relevant documents. While effective, they can struggle with contextual understanding, missing subtle relationships and nuanced information embedded within the data. Reasoning, difficulty in inferring answers that require combining information from multiple sources. Hallucinations, generating answers based on incomplete or inaccurate retrieved information. Knowledge graphs, KGS, like those created in neo4j, offer a structured representation of information as entities, nodes, and relationships, edges. This structure enables semantic search, moving beyond keyword-based retrieval to find nodes and relationships based on their meaning. Reasoning and inference, using graph algorithms, example pathfinding, to derive new information or connections that weren't explicitly stated in the text. Enhanced context, leveraging the interconnectedness of the graph to provide a richer context to the language model. Reduced hallucinations, by grounded generation in a structured data source. 2. Project setup and requirements. 1. Neo4j instance Neo4j or a DB, cloud. The easiest way to get started. Create a free instance at https://neo4j.com/cloud/platform/oragraphdatabase/ https://neo4j.com/cloud/platform/ora-graph-database. Neo4j desktop, local. Download and install neo4j desktop from https://neo4j.com/download/ https://neo4j.com/download. Create a local database. 2. Python environment Neo4j, the official Neo4j Python driver. OpenA, for interacting with OpenA's language models, you'll need an API key. If you want to use another LLM, install the relevant LangChain package. LangChain, a framework for building LLM-powered application. Chromab, a vector database to store the vector embeddings of our knowledge graph nodes. Tick token, for token counting, OpenAI models. Sentence transformers, a library that provide many pre-trained models to create a embedding locally. 3. API keys OpenAI API key get your API key from https://platform.opena.com/account/API keys, https://platform.openai.com/account/API-keys, and set it as an environment variable. Neo4j credentials obtain the URI, username, and password for your Neo4j instance. 3. Data preparation and knowledge graph creation. We'll use a sample dataset related to movies and actors to demonstrate the process. You can easily adapt this to your specific domain. 1 Sample data, movie data. Let's create a small CSV file named movies.csv with the following data. 2 neo4j data loading asterisk. We'll use the neo4j Python driver to load the data into neo4j. Create a Python file named load_data.py. Run the script, python load_data.py. Explanation asterisk. Asterisk we establish a connection to neo4j using the driver. Asterisk the create_movie function constructs a cipher query to create nodes for movies, directors, and actors, and relationships between them. Merge ensures that nodes are not duplicated if they already exist. Asterisk the acted_in and directed_by relationships define the connections between movies and actors/directors. Asterisk the script reads the CSV file row by row and executes the cipher query for each movie. 3 Index creation asterisk. Create index on the node properties to speed up retrieval. 4. Embedding knowledge graph nodes. To leverage vector similarity search, we need to create embeddings, vector representations, for our KG nodes. We'll focus on embedding movie nodes for simplicity, but you can extend this to actors and directors as well. 1 Embedding function asterisk. Create a file named embedding.py. Run the script, python embedding.py. Explanation asterisk. Asterisk we retrieve all movie titles from the neo4j database. Asterisk we use sentence transformer to generate embeddings for each movie title. Choose an appropriate model based on your requirements. All-mini LML6v2 is a good balance of speed and accuracy. Asterisk we create a ChromaDB client and collection. Asterisk we add the movie titles, as documents, their embeddings, and their titles as IDs to the ChromaDB collection. Using the titles as IDs makes retrieval easier. V. RAG with knowledge graph integration. Now, let's build the RAG system that uses the KG and the embeddings to answer questions. Create a file named rag.py. Explanation asterisk. 1 Initialization asterisk. Asterisk we initialize the OpenAI LLM. You can customize the model and temperature. Asterisk we set up the ChromaDB client to access the stored embeddings. Asterisk we establish the connection to neo4j. 2 Get_relevant_movie_titles, query, top_k equals 3, asterisk. Asterisk this function takes a user query and retrieves the top k most similar movie titles from ChromaDB using vector similarity search. Asterisk it queries the ChromaDB collection with the query text and returns a list of the relevant movie titles. 3 Query_neo4j, movie_titles, asterisk. Asterisk this function takes a list of movie titles and queries the neo4j graph to retrieve additional information about those movies. Asterisk it constructs a cipher query that matches the movie titles to movie nodes in the graph and retrieves the director and actors associated with those movies. Asterisk the results are returned as a list of dictionaries, where each dictionary contains the movie title, director's name, and a list of actors. 4 Generate_answer, question, context, asterisk. Asterisk this function takes the original question and the retrieved context from neo4j and uses the LLM to generate an answer. Asterisk it formats the context into a string and then uses an F string to create a prompt that includes the question and the context. Asterisk the prompt is then passed to the LLM to generate the final answer. 5 Main execution asterisk. Asterisk we define a sample question. Asterisk we call get_relevant_movie_titles to retrieve a list of relevant movie titles from ChromaDB. Asterisk we call query_neo4j to retrieve movie details from neo4j. Asterisk we use the results to format the context that provides the language model with the retrieved data. Asterisk we call generate_answer to generate the final answer based on the context. Asterisk finally, we print the answer. 6. Running the RAG system. Run the rag.py script, python rag.py. You should see the retrieved movie titles, the data retrieved from neo4j, and the final answer generated by the language model. 7. Enhancements and considerations. One more sophisticated cipher queries * design cipher queries that incorporate relationships and graph algorithms to answer more complex questions. For example, you could find movies directed by the same director as a specific actor. To node and relationship embedding * embed not only movie titles but also actor and director names and potentially relationship types. This can improve the retrieval of related entities. 3. Fine-tuning * consider fine-tuning a language model on your specific domain data and KG structure for improved accuracy and relevance. 4. Hybrid search * combine vector search with keyword-based search for a more robust retrieval mechanism. 5. Graph algorithms * explore graph algorithms like PageRank, community detection, or shortest path to uncover deeper insights and connections within your KG. 6. Prompt engineering * experiment with different prompts to provide better context to the LLM. 7. More accurate local embedding * while the all-mini LML6v2 model provides a good balance between speed and accuracy, consider using more accurate but slower models, example those from the Sentence Transformers library, for better results. Also, consider fine-tuning embedding model for the KG data. 8. Troubleshooting. Neo4j connection issues double check your neo4j URI, username, and password. Ensure that neo4j is running. OpenAI API key verify that your OpenAI_API_ key environment variable is set correctly. ChromaDB errors make sure ChromaDB is installed correctly. You can delete the Chroma directory to reset the database if needed. Data loading check the CSV file path and format. Verify that the data is being loaded into neo4j correctly by querying the database directly. LangChain errors check the LangChain documentation for specific error messages. Rate limiting be mindful of API rate limits for OpenAI. Implement retry mechanisms if necessary. Inaccurate results make sure that the model is trained on the domain data to reduce the hallucination. This comprehensive tutorial provides a solid foundation for building advanced RAG systems with knowledge graphs in neo4j. By understanding the core concepts, implementing the code, and experimenting with the enhancements, you can create powerful question-answering applications that leverage the structured knowledge within your data. Remember to adapt and refine the techniques based on your specific domain and requirements. Good luck.